So we're working on chapter 11. We've been looking at a lot of vocabulary so far, but now we're going to shift and actually do some math problems. All right. Before we do that, I'm going to give you a real quick reminder from chapter 1 and chapter 4. So we're reviewing a lot as we go here, but we're going to do calculations after we get this refresher here. So first of all, on this page, we're going to be looking at 5 grams of calcium chloride dissolved in 50 mils of solution. And so this will be continuing to be a solution like we've been working on. So we'll have a solvent and then we'll have some solute particles inside of that. We'll talk a little bit more about this glassware and you will use it when you get back to campus for lab again. But this is what we are working with here. So we'll get to that with some calculations in a minute. And everything that we are doing here, you saw something very similar in chapter 4, so you can go back there and review if you need to. So first of all, I want to just remind you that once upon a time you knew how to do your metric conversions. So giants, meat, kings, buying, milk, molding nicely. And that was giga, mega, kilo. This is our base unit, milli, micro, and nano. So you want to remember those. Base units that we're going to see, we'll see things like grams. We'll use this with moles. We'll also use these base units as liters. So those will be a few that we see here when we're looking at solutions. And then just remember with these metric conversions that every prefix here is 3 orders of magnitude different. Remember, if I go from, say, nano to base, then I would count 3, 6, 9. And anytime I'm moving this direction, I'm going to divide by 10. So 1 nano would be 10 to the negative 9th, say grams. And the opposite is true if I move this way. So if I have 1 gram, that would be 10 to the 3rd, 6th, 9th. So 1 gram is 10 to the 9th nanos. So we're multiplying as we move to the right. So keep that in your mind and you'll be using some of these, especially the millis and the kilos in this chapter. Also, calculating molar mass, don't forget, you can go to the periodic table to do that. I could look up calcium, which is 40.08 grams per mole, and then 2 times chlorine. So that's all from the periodic table for those elements, and that comes out to 110.98. Don't forget your units on molar mass. Those are always going to be grams over mole, and it's always per 1 mole. Okay, so this molar mass is going to come in handy as we work some problems on this page. So know your metric, know how to find molar masses, and now we're ready to use that. So molarity you've seen before. It's such a crucial unit for chemists because we can count in moles. We can relate that to formulas and equations, and then we can measure our solution in liters. So don't forget, molarity is kind of a tricky unit. We'll write a capital M, but it's actually representing that there's 2 units in there. So I'm representing that with the blue and the green. So when you calculate the molarity of a solution, you need to have these exact units, moles and liters. So if I want to calculate the molarity of this solution, I notice that I'm in grams, not moles, and mils, not liters, but you're super good at converting at this point. So we are going to use those numbers and convert them and then find the molarity. Something to notice here, there's a couple ways you could make this solution. I could make it in a beaker and I could have a cheap balance and I could be like, it's about 50 mils of solution. When I mix it up this way, I'm gonna get 2 significant figures when I'm done, right? 50 mils, if I'm lucky. Probably I'm not even good with that 50, so I might only have 1 significant figure here. If we want more significant figures, like say you're studying something at a very small concentration, like lead in water, you need to use equipment that can give you more significant figures. So here, I would use a more expensive balance to get more digits. And then I would use this piece of glassware, which is called a volumetric flask. And a volumetric flask only has 1 marking on it, and this 1 marking would be exactly 50.00 mils. So I use it to measure 1 exact measurement. But the benefit is, instead of having 50-ish mils, now I have a lot more precision and accuracy if I use this tool. So we want to make sure we pay attention to our significant figures here. This will cost more and take more work than the beaker, so we want to make sure that that cost and effort shows up in our calculations. So calculating the molarity. So I need to get to moles and liters. So 5.00 grams of calcium chloride. Grams need to convert to moles, and I have that molar mass over here, right? 110.98 to 1 mole. Grams cancel, and when I work that out, I get 0.045053 moles of my calcium chloride. I should have here 4 significant figures, and I just kept an extra one so I don't round too much as I work. All right, 50.00 mils. I need to convert my mils into liters so that I can use it in molarity. So here's my milli. If I have 1 milliliter, then I need to divide by 10 3 times to get to the liters. So that's 10 to the negative 3 is that divide by 3. So then I do this problem. Remember, the metric conversions are exact, so they don't affect your sig figs. And this is going to come out to 0.05. And remember, this 0 and all the trailing ones after the decimal are all significant, so keep all 4. There's my liters. Now I have moles and liters. Now I can plug it into molarity. 0.045053 divided by 0.05000 moles over liters. And if you can keep in perspective what we're doing here, this is my moles of solute. This is my liters of solution. So the green solutes and then the blue volume. And I want to have 4 sig figs at the end here. So 0.9011 molarity. And I always want to say what the solute was. So you want to make sure that molarity that communicates both moles and liters is telling me what solute you're talking about. Now over here, if instead of using this better equipment, I had just done it in a beaker, I have 3 sig figs and then 2, if that even. So I would get that same number if I did these calculations, but it would be 0.90 molarity. And that 0 even, depending on the quality of that 50, it might just be more like 0.9. So huge difference. In one setting, this might be enough, so you can just do the quick, cheap way. But in a more precise analytical setting, then you would want more significant figures. So that is a reminder here and how to solve for molarity. We're going to come back on the last video here and watch dilution and molality.